Good afternoon, everyone. We are happy today to present you our paper about end-to-end security validation of IoT systems based on digital twins of end devices. This paper is the result of a joint work between Airbus CyberSecurity and STMicroelectronics in the context of the Edge 2020 project Brain-IoT. What are the main challenges in the IoT? The first one is that we have a lot of heterogeneity in IoT system architecture, either from the network or the applicative point of view. And this heterogeneity makes it very difficult to set up processes for overall system validation. And it's also very difficult in this context to ensure a full end-to-end security layer. The second main challenge is that most of the IoT devices come from the mass market. Indeed, one of the revolution of the IoT is that we can collect lots of data, but this means that the devices that are coming from the mass market have not been designed for use cases that requires a little bit more of security. So this is also quite a high challenge for the IoT. And finally, the last one is about the heterogeneity of the constraints. Indeed, we can see that we are using IoT systems in many use cases, from the Industry 4.0 to the connected transportation, for example. And as these IoT use cases are broad, there is also a lot of different hardware that have very different constraints. So now, what is the typical IoT system architecture and what are the relative threats? We take here as an example an IoT system architecture composed of 5 main components. The first one is the IoT device itself, that will collect data and interact with its environment. The second one is the edge layer, which allows the connectivity at the IoT level. Then you have the network provider, which will connect the IoT system, the IoT connectivity layer with the rest of the world. Then you have the IoT platform, which collects the data from different IoT system and IoT devices. And finally, on the top of that, there is the application and the services that will collect and analyze the data. On each point of this architecture, we have security threats. It could be hardware security threats, for example, such side channel attack or dumping on the IoT devices itself, but it could also be network threats with device spoofing, for example, or backend spying into the network provider, for example. So all those threats, in order to ensure the security of the system, we need to set up end-to-end security. If we look a little bit at the end-to-end security layer that exists today, we see that there is the legacy solutions, the legacy layers such as TLS, for example, but that does not fit at all to the IoT constraints. So we have seen last year's some initiatives that are very interesting and show that we can improve the existing layers in order to allow it running on IoT devices. But there is still a missing point, which is how can we ensure the security on the top of any kind of applicative protocol. For example, if we take an IoT system based on LoRaWAN and MQTT protocols, most of the time you have all the data that are going through the LoRaWAN protocol, which has its own security. And then all is decrypted and proposed through MQTT layer to a final services. But this means that the MQTT server will have the data that will go through the server in clear text. And this clearly is a lack of end-to-end security, because if this MQTT server is hacked, then all the data will be available. Finally, that's why we have worked in the context of a Brain-IoT project in an end-to-end security layer able to ensure the security, the encryption and the authentication of the data on all the data value chain, including through very constrained protocol. This layer ensures the encryption and the authentication. It means that when the data are going through the third-party servers, such as MQTT server, HTTP server, they are fully encrypted. So there cannot be any leaks of the data, and it cannot be understood by a hacker. This security layer has a very low impact in terms of energy consumption, and have a very low impact on the bandwidth, and therefore fully fits the constraints of the IoT protocols. But as we said in the introduction, one of the main challenges of this kind of system is the validation. How can we validate this security layer on a high number of devices and a high number of environments?
We are considering this IoT architecture frequently used in many deployed IoT systems. It is composed of the end devices on the left, such as water meters or water stations, a LoRaWAN communication system, and the middleware, which is in this case SensiNact, that is connected to the application dashboard. In this architecture, the data gathered from the sensors are encapsulated, encrypted, and sent by a LoRaWAN transmitter. The gateway recovers and sends them through internet till the LoRa server that activates the end devices and decrypts data transported by LoRaWAN. These data are sent to the business application through the MQTT protocol. Then, the middleware is in charge of decapsulating the useful data and storing them in a database for data analysis. Finally, the processed data are displayed in application dashboard for the end-user exploitation. In our developments, we have decided to perform the communication as an abstraction of all the communication data path by using HTTP requests from the end device to the middleware through the network. This choice was done considering that the main development goal was the integration and validation of the end-to-end data security. In the LoRaWAN examples presented in the paper, the communication data paths, LoRa elements, transmitter, gateway, LoRa server and MQTT are abstracted by the HTTP protocol. Let's now focus on the end device architecture. It is typically composed of a microcontroller, one or several connectivity elements, and one or several sensors or actuators. The main issue is the verification of the embedded software in charge of the data gathering from sensors, the local processing of data, formatting and analysis, power management, payload construction and encryption, and at the end the transmission of the encrypted data or metadata using the device connectivity capabilities. We have developed a refinement methodology based on digital twins of the end devices at different levels of abstraction. Let's now go into the details. The black box model is an abstract representation of the end device. It is a service-oriented model that represents its functionality regardless of the internal architecture that implements its behavior. It can be considered as the functional reference of the end device. The black box model can be reused whatever the implementation choices, or even in case of replacement of the physical device by another one, as long as the functional specification and interfaces remain unchanged. It provides the functional contract. The other models or the physical device shall comply to. This executable model is implemented in Python in our work. This is a non-ambiguous, repeatable, and deterministic model of the end device specifications. It takes as input a file containing the data values that would be obtained from a sensor operating in real conditions, and generates the HTTP requests to the network. The black box model provides several benefits. It is available very early in the design process, it is very fast, it can be easily distributed to all the stakeholders of the project, it is used to validate the hardware and software developments, and end users can quickly prototype their system and create large-scale mockups. The second step of the refinement methodology is the creation of a white box model of the end device, representing the internal architecture of the device. This model is developed using the System C TLM IEEE 1666 standard. The microcontroller model is an instruction-accurate model of the core that represents the bus transactions initiated by the processor. All peripheral models expose register-accurate interfaces to support read-write transactions by the embedded software and implement the behavior of the block to offer a functional simulation. It executes the embedded software that will run unchanged on the physical device. A software debugger is connected to the microcontroller model to support interactive debug activities. The sensor model serves I2C requests issued by the microcontroller and implements the behavior of the block to react to the programming sequences. The environmental data injected in the black box model are reused to feed the sensor model, keeping the stimuli unchanged for validation purposes. The connectivity model serves SPI or UART requests issued by the microcontroller and implements the behavior of the block to react to the programming sequences as well. It sends the payload over the network as an HTTP request. The benefits are the following. System verification can be achieved in advance without the debug limitations inherent to physical devices. The models offer full inspection and observability capabilities for debug and analysis. The complexity of large-scale systems from tens to thousands of end devices can be addressed by instantiating the appropriate number of models in the simulation platform. The system reliability is increased as scenarios focusing on device robustness can be added to consider its interaction with the system environment. Last but not least, embedded software updates can be validated at the system level before deployment in the field. Let's now consider how to add end-to-end security in the system. It requires to work both on the end device and on the middleware. First, on the black box model, the security module is used to encrypt the data payload to be transmitted to SensiNact through HTTP. From an implementation perspective, the security module is delivered as a compiled library providing C functions. In this work, the library is wrapped to call the encryption function from the Python black box model. Once the payload has been encrypted, the black box model continues its execution as when the data are not encrypted. As the encryption step is added in the data flow, it can be easily switched on or off for debug purpose. Let's now consider the white box model. Adding security in the white box model consists in adding in the embedded software running on the microcontroller model the calls to the functions of the C encryption library of the security module. It encrypts the payload eventually passed to the connectivity model. All the rest of the embedded software remains unchanged. Consequently, it is very easy to support both unsecure and secure communication modes, for instance for debug purposes. Now, on the middleware side, adding security in SensiNact means that the security layer decrypts and checks the integrity of data received. To perform those actions, an SDK was developed to integrate those functions in the final application. The SDK is composed of the next four main components: an enrollment module. In case of unknown device, this module performs self-enrollment operation and returns an encrypted AES ciphering key used by the device for future communication. Device status check. This module checks whether the devices have been revoked. Then the authentication and integrity check. This module checks the message integrity and the device stateless authentication using public device identity and the corresponding secret key. Last, the decryption module. This module decrypts the payload and forwards the clear text message to the application dashboard through the database. As a conclusion, embedded software, security implementation and validation are non-trivial, time and resource-consuming tasks. They require a high level of expertise. The problem is very well known and is exacerbated with the deployment of IoT systems. This paper has presented a design methodology approach to relieve this problem, reduce design and validation times, increase the quality of design, ensure better performances of the overall system, and finally facilitate the scale-up of the number of end devices by using the digital twin concept. Last but not least, this proposed model-based approach allowed the implementation, verification, and validation of an end-to-end security solution in few weeks, thanks to the debug capabilities and full observability provided by the models. Thank you for your attention.